Hello everybody, welcome to this week's Astro Coffee Hangout. My name is Tony Darnell, I'm from deepastronomy.com, and today we are going to be talking about Jupiter's moon, Europa. It turns out we're going there, and no, we're not even listening to Arthur Clarke's warning about it. We're just going to go. We're just going to go and see what there is. We've got a mission in the works, and I've got my guests with me today who are members of the Europa Clipper mission, and they're going to talk to us about what their work is doing, what they're going to be doing on the mission, as well as some of the properties of this moon and why it's so interesting. And I know you guys have been asking for a hangout like this for a long time, and my very good friend and colleague, Dr. Carol Christian, has put this together. Hi, Carol. Welcome.
Hey.
Hi.
Hello. How are you?
I'm doing real well, thank you. Let's start by doing what we do each week. Let's talk about these hangouts, what we're trying to do very briefly, and who is making this possible.
Sure. Okay, so we had this idea when we were sitting around chatting at our own science coffees. Wouldn't it be fun to invite interested people into our discussion? But what we tend to do is we talk about other people's papers unless we have a guest at our institution. And we thought it would be kind of boring if you just listened to us, Tony and Carol, week after week, talk about somebody else's research. I don't know. That'd be okay. It might be funny, but it would be much better to actually talk to the actual people doing the work who have the ideas, got the results, how they got their observations, what they're thinking, what they're going to do next. We love to talk about missions. And so we started afternoon astronomy coffee hangouts. They're twice a month. And they are part of a series that also includes Footsteps to Mars and Future in Space. And they are sponsored by the American Astronomical Society and the American Astronautical Society to represent the astronomers and the engineers involved in this exploration of our universe. So that's what it's about. Grab a cup of coffee, tea, or your beverage of choice, and join us on the Hangout and send us some questions.
That's right. I'm looking at the live chat on YouTube right now, and already some people have iced tea. I also have iced tea. That's what I'm drinking as well. So we are going to be talking about Europa today. So there are lots of ways you can interact with our guests. I, for the first time, am streaming on 4 platforms now. We've got YouTube, Twitter, Periscope, Facebook, and Twitch. So I'm on all 4 of those right now. So if you are on them, I'm looking at the chat on YouTube as well as Twitch. So please send us your questions and comments that way. We also have with us Carl Clarke. He's going to be monitoring a lot of the social media channels for us as well. How do you say your handle? It's Metz on Young, is that right?
Yep, Metz on Young.
Okay,
good. It's homage to a friend of mine and an artist.
Okay, well he's the one on the social media with that handle. You're also looking at Twitter, right? Using the hashtag Astro Coffee, right? Okay, so
yes, I am.
All right, I will check in with you a little bit later. So let me go ahead and get to our guest. My first guest is Dr. Melissa McGrath. She is a senior scientist at SETI. Wait a minute, let me actually select you. There you go, so that you come up. She's a senior scientist, and she is a co-investigator on 2 of the instruments on the Europa Clipper mission. Hi, Melissa. Welcome to our Hangout.
Hello, nice to be here.
Good. It's really great I can't wait to start talking to you. Also with me is Dr. John Spencer. He is an institute scientist at the Southwest Research Institute. He is also heavily involved in the New Horizons mission that flew by Pluto, but now he's also a part of the extended mission, which is going to the Kuiper Belt. Hi, John.
Good afternoon.
Just real quick on the New Horizons mission. Are you guys kind of in a hold mode until you get there, or do you still have a lot of? You're probably looking at a lot of data, aren't you?
We've got lots of data from Pluto, and we've got lots of work to do to get ready for flying by this little Kuiper Belt object in 18 months now. We are about to make decisions on how close we'll fly to it, and we're working out all the details of all the pictures and other data we'll take when we get there. So yeah, it's a very busy time.
Okay. Well, let's start with this mission to Europa. So, who wants to tell us? Maybe Melissa, you can give us some background on what this mission is going to be about and what sort of timeline we're looking at.
Yeah, it's going to launch in the early 2020s. It's been in works at NASA for a long time, really, since the missions Voyager and Galileo have flown by in past years and made really interesting discoveries about Europa. In particular, that it's thought to have a subsurface ocean that has a lot more water than the Earth's ocean. And so because it has a lot of water and some of the chemicals and energy that we think are important for life, we think it might be a potential abode for life in the solar system. And so NASA had made it a high priority some years ago to get back to Europa, and we're in the planning stages. We have a mission planned. We have instruments selected. The mission will fly by close flybys of Europa about 50 times over the course of a number of years. The spacecraft will actually be in orbit around Jupiter. We'll make many close flybys of Europa to allow us to do lots of observations.
So this mission is not going to land on Europa. It's just going to fly over it.
No, there's actually a second mission that's not quite as far along, but for which instruments are just about to be solicited that we hope will land on Europa. And so we'll get there a little earlier, do a little reconnaissance, and then hopefully a lander will come along a little after us.
Okay.
So there are plans to land too.
Okay, and John, how about giving us a little insight into what your role is on the Clipper mission?
Sure. I'm on a couple of instruments. I'm on the ultraviolet instrument along with Melissa, which will be looking for the ultraviolet glow from Europa's atmosphere and potentially from plumes and other things that it can do with the environment around Europa, maybe tell us something about the composition. I'm also on the infrared mapper that will be mapping temperatures on Europa, which we're very interested in because anywhere where there's activity, where there are cracks in that ice shell, there might be heat coming out, or if the ice shell is particularly thin. And so we're looking for hotspots on Europa that might tell us where the activity is, where potentially places where we might want to land with our upcoming lander. Plus we learn about how hard the surface is, how many rocks there are on the surface, all kinds of other useful things.
Okay, well that's good. So that's a good segue into what I wanted to ask you next. Give us a little some Europa 101. What's the moon like? You've already mentioned it's got some of the properties, icy crust, and maybe even has cracks in it. Are we really sure there's water there, liquid water underneath the crust?
We're pretty darn sure at this point. There's quite a few lines of evidence, and they all point in that direction. We know the surface is water. It's frozen water. It's ice. It has a very distinct spectrum that we can measure from the ground or with spacecraft. And so it's a slam dunk that the surface is made, at least in large part, with ice. We also know that Europa is electrically conducting because we see how it influences Jupiter's magnetic field. And it has to be pretty conductive in there. And just ice on its own won't do that.
So wait a minute.
Properties.
The magnetic field of Jupiter is affected by the electrical conductivity of Europa?
Exactly.
In a way that you can actually see.
Right. We measured that with the Galileo spacecraft flying by Europa.
And anybody who's ever tried to shave in the bathtub knows water's pretty good at conducting electricity, right? So,
right.
So that's another piece of evidence that this has water around it. How thick's the ice crust?
Well, that's a big question that we don't have a good feel for yet. We think it's probably more than a kilometer or two because we see craters and things that have been dug into the ice that are about that deep or were about that deep when they formed and don't appear to have broken through. Some people would say, oh, those mean it's really maybe 10, 15 kilometers deep. But it can't be, the total amount of water in Europa is only about 100 kilometers thick. And so if there's liquid there, then the ice has to be less than that thick to make room for the water underneath it. And so it's somewhere, tens of kilometers, maybe a few kilometers. We don't know any more than that. And one of the main reasons for this mission is to try and understand that better. How thick is that ice? How easily could we get through it if we wanted to? Okay,
Melissa, can you comment on that? How are we going to find that out with the Clipper mission? What sorts of ways can we probe the ice
Oh, there are a lot of different ways. The first way is just the way we did it with Galileo that John already mentioned, and that is that we'll measure the magnetic field close to the satellite, and we'll be able to tell how conductive, how much water there is perturbing the magnetic field of Jupiter. There's also a radar on board that sounds the surface of the satellite and subsurface as well. And that's another way to tell what the surface is made of, whether there's liquid below the ice. And then, we'll just take pictures, right? If there's water oozing out or things cracking in real time or plumes erupting, we should be able to see them because we'll have much finer resolution imaging over the whole surface of the satellite than we were able to achieve with any of the other missions. And really all the instruments make measurements that bear directly on the questions about the surface, what the surface is made of, if there's current activity, and all those things bear on whether there's an ocean there or not.
Okay, well, what about the effect of the planet Jupiter on the moon itself? I'm thinking we've got an ice crust. We don't know how deep it is, but we know it has one. There's probably liquid. We have a good idea. There's liquid water under there. In order for it to be liquid, though, there has to be some kind of way to keep things warm, right? So I'm trying to think of what sources of heat there might be, and one of them comes to mind would be the tidal forces of Jupiter. Is that a way to warm up the planet?
Exactly. Yes, exactly. That's one of the primary ways, right? Probably the primary way.
Okay, it is the primary one then.
Like Io, the innermost Galilean satellite, Europa, and Ganymede, they're all in resonance. And so,
could you explain what that means?
Yes. Io does one orbit. Io does 4 orbits. Europa does 2 orbits, and Ganymede does 1 orbit in the same length of time. And so they line up with each other at particular times, and that creates what's called a resonance. And it's really that resonance with the gravitational force from Jupiter that causes tides, and tides, especially on Io and Europa, provide a lot of energy. On Io, we know it has very active volcanism, more active than any other body in the solar system, and we can easily see eruptions happening all the time. On Europa, we think the same kind of thing is happening, but it's a little more muted. There's a little bit less energy available for Europa, and it's a little colder. Europa's a little colder, and so it's icy. And so it's a slightly different kind of activity. We don't see huge volcanic plumes on Europa like we do on Io, but recently there have been several observations made with the Hubble Space Telescope that give us indications that there are these erupting geysers on Europa, just like on Io. They're just a little bit smaller scale, so they're a little harder to see.
Okay. So really then, it seems to me like the liquid water from Europa probably wouldn't be there if it weren't around Jupiter, right? If it were just out there on its own?
That's...
I'm gonna, John, why don't I let John comment?
Okay, John, why don't you comment on that?
I think we would have said a pretty solid yes to that a couple of years ago. Now, of course, we've flown past Pluto with the New Horizons mission, and we've seen evidence that Pluto might have a liquid ocean beneath its surface. And Pluto isn't orbiting a giant planet. It doesn't have that extra tidal heat. It's purely living off the radioactivity within it, which is a very small amount of heat. So we have evidence from Pluto that maybe you don't need the tidal heating to have an ocean, but the ocean on Pluto is probably a lot deeper. It's
deeper under the surface.
Under the surface.
Yeah.
The ice is probably mostly frozen with just a narrow layer of water near the bottom. Much further from the surface, much less likely to have the kind of energy you need to support life. So it's a very different kind of beast. And also, a lot of Pluto's surface is quite old. It's covered in large craters, which Europa has almost no craters, just a scattering of small ones, which suggests that that surface is pretty recent. And due to this tidal heating, that surface is being continually destroyed and renewed. and that ocean is therefore communicated with the surface in some way to destroy those craters as they're formed. So Europa is certainly a much more active world than Pluto is, at least in the interaction of the ocean with the surface.
Okay.
I'm just going to jump in and also, I'd hate to not mention Enceladus, the moon of Saturn that also,
that's right.
Now erupts. It's an icy world. And, what we're really finding now is that these icy worlds across our solar system and perhaps elsewhere, oceans seem to be common on these worlds now. And so I think we wouldn't have suspected that a number of years ago, but we're finding that that's the case.
There's a lot of water out there, isn't there?
There is.
All right. Well, I want to ask a question from Philip W. He's on the YouTube chat, and I'm going to use this question to lead into the instrumentation on Clipper. Question for the panel: could Clipper's e-Themis system be used to map where the thermal heat in the moon is coming from? First, tell us what e-Themis is, and then I'll ask about other things.
Sure, I'll take that because that's one of the instruments that I'm working on.
Okay.
So that is the thermal mapper that is going to be measuring temperatures across Europa on the night side and the day side. And one of the prime goals is to look for evidence of heat leaking out of the interior of Europa. We might see broad areas of elevated temperatures where the ice is relatively thin and the heat is conducting through from water underneath. Or we might see, as we do on Enceladus, narrow cracks that are hot or warm because gas is leaking up through those cracks and is warming the ice on either side. That's what happens on Enceladus, where we see these very spectacular.
Okay, but wait a minute. Hold up your prop that you have with you there, and show us that. Yes. This is. Yeah. Okay, I want to work this in. Let me get you full screen here, so let me get rid of all this. Okay, so this is a 3D printed model of.
This is awesome.
Europa, which I have to say is really great. Mm-hmm. But I'm seeing cracks on there.
Absolutely, okay. Yes. Europa is covered in cracks. It's got, some of them are huge. You can see ones on this model that go pretty much halfway around Europa from one side to the other. But as you get into finer and finer detail, there's just a complete network of overlapping cracks running in all directions. And so this ice shell is cracking very easily. That's one reason we think that the ice might be quite thin, because it cracks so easily. And some of these cracks just look like simple fissures. Some of them actually have ridges built up along either side of them, maybe as though something has come out of those cracks and deposited on either side. So there's lots of cracks. What we don't know yet is how many of these, if any, are active at the moment, are actually connecting down to the warm material below and are maybe have heat coming up along them or gases coming up along them.
Okay,
so that's a big job of ours.
You have had hints from previous spacecraft that there are warmer regions?
We certainly have. And I'll let Melissa talk about some of the recent evidence from Hubble that there are cracks that are letting gases out. But in the Galileo data, I was on the instrument that was mapping temperatures on Galileo. It was a much cruder instrument, didn't have anything like the detail we'll get from the Europa Clipper. But it did see some pretty interesting variations in temperatures, particularly at night. And there is a broad, warm region on the night side. I can even point to where it is. It's kind of right about here above this bright spot, which is a fresh impact crater. So it's kind of around here is a region where it was warmer than the rest of the surface at night. And so we don't know if that's because the crust is thin there and heat is getting out, or maybe that region is just more densely packed and can store heat from the daytime better and radiate that heat.
What we believe to be the little silhouettes of plumes. So that was the first paper published in 2016. But the real exciting thing is that recently we see what we believe to be a repeat detection of the same plume, roughly the same location. That alone was exciting, But when we compared the site of that eruption to the thermal map from Galileo that John talked about a minute ago, and he showed where there was this higher temperature on the night side, it turned out that these two repeat detections fell exactly on top of this thermal anomaly that was observed by Galileo on the night side. And so I think for the first time, you know, we're accumulating enough evidence that people are beginning to believe that there really is activity ongoing, that we're finally able to start getting a handle on it. And so there's starting to be a fair amount of evidence. And the key, you know, in science is always repeatability. And so the fact that we've seen a repeat of the same eruption and that it coincides with a thermal anomaly seems to be pretty strong evidence that there's exciting things going on Europa.
Yeah, cool. Well, okay. Well, while I've got you here, then why don't we move from that? And we were talking about ETHEMIS. You are working on two of your instruments. Tell us a little bit about those that are going to be on the Clipper spacecraft.
Sure. The first one I'm working on is the ultraviolet instrument, which is really very similar to the Hubble instrument that was used to detect the first eruption on Europa. And it observes emissions from different species in Europa's atmosphere, and in particular, you know, water species, hydrogen and oxygen. And so the UV instrument will be one of the primary plume search instruments. In addition, it can do stellar occultations, that is, follow a star as it passes behind Europa. And those measurements can be used to determine very precisely the composition of the gas near Europa. And that, we believe, comes from active eruptions. And it's it's a way to get a handle on what possible species there are in Europa's ocean. And then I'm also a co-investigator on the mass spectrometer. It's called Mass Specs. And the mass spectrometer makes what we call in situ, that is local measurements of gaseous species near Europa. Again, we think those species come from eruptions that come from the ocean ultimately. And the mass spectrometer is a very sensitive way to measure the most abundant species, but also very minor trace species in the gas near Europa. And that can really help give us a handle on what the composition of the ocean is, what the chemical evolution of that ocean might be, what the chemistry going on in the ocean now might be. And all those things are very important keys to trying to understand whether there might be life in the ocean on Europa.
Okay, good. I want to get back to this question of life here in just a minute. But so, did you tell us earlier in the Hangout? I might have been distracted by all these chat things I've got to get. That the Clipper mission is set to launch when?
I think the current launch date is 2023. It's early 2020s. So 2022, 2023, 2024, or something like that.
And
That's the current plan.
And it'll take a few years to get there, right?
It does. And we're not absolutely positive which launch vehicle we're going on yet. Depending on the launch vehicle, we can either go there directly, which is, I believe, 5 years, or we may have to take a more circuitous route, which could take several more years. So it'll be something like 5 to 10 years to get there.
And how does that get decided? What launch vehicle is it? Money? Do companies need to bid, and then you decide on the rocket that way?
It's really the availability, and so I believe what's baselined right now is the SLS, the new space launch system, the big rocket that NASA's building. And so it's really whether that rocket's going to be ready in time and whether it's been used enough to be reliable enough. And I think the answer is yes. I think that's what's going to happen, but it's a little hard to say since SLS hasn't even had a single launch yet.
Okay. All right. Well,
do you mind if I jump in real quick?
Yeah, go ahead, Carl.
SLS factor?
Yeah, go ahead.
I know that in the latest Authorization Act that was signed in February, that at least the committees in Congress, the Senate and the House, are wanting the SLS. They're really pushing for it. But from what I've also been able to kind of glean is there's going to be one for EM1 and then one for EM2. So where they're going to get the third vehicle, because I know they don't want to postpone EM2. That's going to be a question in EM2. EM is exploration mission. Those are the crewed, the manned human exploration missions. So there's a little bit of crossing the streams going on there. So
yeah, we'd really like to use SLS because it's such a powerful rocket. It can take us straight to Europa in 2 or 3 years, whereas with the smaller rockets that we would otherwise be using, I think a Delta IV Heavy, which is still a big rocket but not like SLS, don't have the power to take this rather large spacecraft directly out to Jupiter. We have to fly past the Earth and Venus a couple of times. It's a longer flight time. The spacecraft has to be able to survive not only the cold of Jupiter, but the heat of Venus. And so that makes the design a little bit more complicated. So there's quite a few reasons we'd like to use SLS if we can.
Okay. I just want to comment real quick. There was some issues with the YouTube stream, and apparently it's been worked out now. I saw a dip myself, but the other streams did not suffer from that, folks. So if you're seeing trouble on YouTube, you can head over to Twitch. The Twitch seems to have a pretty good stream going there. So thanks for hanging in there. So let me see if I can find. Venom7111 is asking, since it experiences external heating, would Europa's core be liquid or solid from pressure?
It's probably solid. The pressures inside Europa are a lot less than the pressures, for instance, inside the Earth, because Europa is only a quarter the size of the Earth. And the rock inside the Earth, which we don't know if similar in composition to the rock inside Europa or not, but it certainly would behave somewhat similarly. So I think the rock inside the Earth is solid most of the way down to the deep interior, and that would be the case on Europa as well. And I should clarify that Europa is basically a ball of rock with a thin shell of ice around it. And so the deep interior is made of rock. It may be kind of soggy rock that's got all this water permeating it, but it's definitely some kind of rock down there underneath the ice.
Okay.
Yeah, I agree, and I'd also just add that the same Galileo measurements that helped indicate they're an ocean, the reason they can do that is they tell you about the interior structure of the satellite. And so both the magnetic field measurements and also the gravity measurements as a spacecraft flies close to a satellite, they do allow you to get information about the interior composition. And so the models of the data that's been gathered show that Europa probably does have a rocky core, just like John said.
And in a related question, Hugo Burnham on Facebook is asking, do we have any evidence that the surface of Europa is moving around in any kind of plate tectonic kind of way?
Mm-hmm. Yeah, we certainly do. Coming back to my prop here, it's a little hard to see on this scale. In fact, I don't think there's any really good examples. But if you were to zoom in on this region here, there's a whole network of cracks. I'll get up close to the camera so you can see the
Europa in your face.
Yeah.
Whoa! Thanks for that.
You can actually you can take those images and you can do jigsaw puzzle exercises, and you can actually rearrange things and put things back together that have been moved apart, and you can have things match up along the edges. So just by looking at the pictures, you have really good evidence that the surface has cracked and has moved apart, and material has welled up in between those plates and filled in the gap, which is a lot like what happens with plate tectonics on Earth. Though on Europa, it seems to happen on a much smaller scale, tens of miles instead of continent scales that you see these motions. Okay. So yeah, we think we don't call it plate tectonics because it's really very different materials and probably very different in detail from what happens on the Earth. But the basic idea of rigid blocks that move around is definitely seems to happen on Europa as well.
Okay, well, in a related question, well, it's not really related to plate tectonics, but George Caldwell on Facebook is also asking, does Europa have any sort of magnetic field, or is it too small to retain its own? Now, we talked about Jupiter's magnetic field and the effect that Europa has on it, but does it have one of its own?
From what we know, it doesn't. it has this ocean that circulates around, which creates an electrical current, and you can model the observations pretty well with just a Jupiter field that's perturbed by this electrically conducting liquid. And you don't need to put in a magnetic field from Europa. So as best we can tell, it probably doesn't have its own intrinsic internal magnetic field.
Okay. And so I just want a quick thank you to Bernie Upton and you guys for sharing this video on Facebook, so it's getting out there to more people. So thank you very much. Bjorn Larson is asking, how much energy does Europa's tidal energy generate compared to sunlight on Earth? How much energy does Europa's tidal energy generate?
Well, it's pretty small. The Earth absorbed a huge amount of sunlight. We're 5 times closer to the sun than Europa is, of course. But sunlight heats the surface of objects, and that heat is immediately radiated away. And it doesn't do much in the interior. It just sort of generally warms the whole of the interior. But if you want to actually generate geology, you have to have heat that's coming from inside. So shining a light on the surface, even though there's a lot of energy involved, that heat doesn't penetrate down enough to get geologists going in the interior. So it's a little bit misleading to compare the total amount of energy. There's a lot more sunlight, but it has a lot less effect on what happens in the interior.
ADW was commenting, man, I wonder what it would cost to have a scale Jupiter made to that Europa law. Carol's going to print
I need a bigger office.
Yeah, Carol's going to print out the Europa one. I wonder if there's a Jupiter one. She'll print that out too.
Well, maybe we can just do part of the surface. That'll work. Yeah.
Well, we could just do the whole thing, but make it smaller scale.
Yeah.
You know.
Okay. Yeah.
Make it so it'll fit in our office.
Yeah. Exactly.
That would be so cool. I mean, the Juno results showing the clouds on Jupiter are just fantastic. It would be great to have that in a 3D printed globe.
I know. I've been seeing some amazing videos lately from the Jupiter mission. Yeah. So yeah, or Juno mission.
Be awesome.
Yeah. Philip W., could the solid core of Europa be? Is it breached by the subsurface ocean, and would that affect the orbit of the moon? I'm not quite sure what he means by breached. The subsurface.
Well, so no. I'll comment first very briefly, and then John's a geologist, so he's probably better qualified than me. But Europa's surface, the ice is really just a thin layer on the outside, and the same with the ocean. Even though there's more water than the Earth's ocean, it's a relatively thin layer compared to the overall radius of the satellite. And so thin ice, relatively thin ocean, and then you just get layers of rock like on most of the rocky planets. And so there is, some chemical interaction and energetic interaction at the base of the ocean where it hits the rock. And that may be a place where, like on Earth, at the base of our oceans, there are these chimneys and smokers and places where there are chemical interactions taking place. That may be going on Europa, but the water is very unlikely to penetrate very deep into the interior of the satellite.
Okay, and a real simple question from Grote. I can't pronounce it, dude. I'm going to try and do it. Jank. No, I'm not. I'm just going to call you Gront. Does Europa have seasons? Does Europa have seasons?
It has only very subtle seasons. Europa is spinning on its axis like any other world, but the tilt of the axis is the same as the tilt of Jupiter's axis, and it's only a few degrees, about 3 or 4 degrees, compared to the 23-degree tilt of the Earth's axis. So the sun is always very close to Europa's equator, and it just barely grazes, well, I can use my propaganda, it will just barely graze the North Pole here, or just barely graze the South Pole here as it moves up and down just a little bit. A bigger effect on Europa, actually, is that Jupiter's orbit around the sun is eccentric, and it's sometimes about 10% closer to the sun than at other times. And so when Jupiter, and therefore all the moons, including Europa, are closer to the sun, the surface gets a few degrees warmer just by being closer to the sun, and then cools off a bit as it goes away. And we'll look to measure those effects with our thermal instrument as well.
How long is a Jupiter year?
It is 12 years, 12 Earth years.
Okay, now does that factor at all into the mission that you're launching? I mean, do you care where Jupiter is in its orbit?
Absolutely, we care. It makes a big difference whether Earth and Jupiter are on the same side of the sun and therefore close together, or whether Earth's here and Jupiter's on the other side of the sun. It's
costs
exactly
a bit more
the
to
same.
get there.
It's exactly the same as with Mars. When we launch to Mars, we always launch when Earth and Mars are on the same side of the sun and therefore as close together as possible. And so we want a launch that minimizes the trip time. And so we want to launch when Jupiter is as close as possible to the Earth.
Okay.
And it makes a big difference.
Okay, that would help if you want to get there quickly and save a little money and stuff. But what about scientifically? Is it more interesting to be there when it's, say, closer to the sun or not? Or do you really care?
It doesn't make a lot of difference, no, because those effects are fairly subtle. You don't have the big seasonal effects that you do on the Earth or even on Saturn. Actually, talking about Jupiter's year, I'll just throw in a fun connection between seasons on Jupiter and Chinese restaurants.
Okay. Yeah, of course. Let's do that.
You go to a Chinese restaurant and you see the menus that have all the Chinese zodiac and all the 12, the year of the rat and the year of the sheep. And
yeah, I'm the year of the tiger.
Right. The Chinese zodiac is based on the motion of Jupiter. So Jupiter is moving around the sun in 12 years, and in each year it's moved a 12th of that orbit, and that's controlling the Chinese New Years are basically controlled by where Jupiter is in its orbit. I
did not know that. Wow. Talk about astronomy you can use, folks. That's awesome. I did not know that. That's really cool. Okay. Well, so let's, we've talked about what Europa's like. We've talked about Jupiter. We've talked about the Clipper mission going there. Now I want to talk a little bit about life on Europa. What do you guys think? Are you just not going to give us an opinion? If, first of all, I think, and I got to, let me start this little segment off with an email I got from Herbert Winehandel, who was watching our hangout we did a couple of weeks ago with the Cassini folks on the JPL, and he was referring to a comment made by Dr. Morgan Cable, who said that Dr. Cable's statement that the hydrothermal vents are independent of oxygen is incorrect. All multicellular creatures like worms, crabs, mollusks, shrimps are needing oxygen to live, grow, and reproduce. And he's saying that the only single-celled anaerobic bacteria are able to live without oxygen. He's making the point oxygen is important. So, what do you think about the oxygen levels? First of all, if there's water, there's oxygen because of the water molecule, but what do you think about its ability to harbor life, these oceans?
Do you want me to go first, John?
Sure. Then I'll add something.
I'm optimistic myself, and I'll tell you why. First of all, there's plenty of oxygen. There's no problem. There's lots of water and lots of oxygen, and we think the same kind of rock-water interaction could happen at the base of Europa's ocean as happens on Earth. And so, I think that even in analogy with Earth, it's not unlikely. But my thinking is a little different, and that is that we didn't ever really think extrasolar planets might be really common, and now we know they're really common. We didn't think that there were lots of icy ocean worlds in our solar system, and they're turning out to be common. I think that we can't even imagine the possibilities, and so I'm just optimistic because I think that wherever we go, we find things are so much more complex and interesting and unexpected than we believe. And so I think the same thing is going to be true on Europa. It's going to surprise us, and it wouldn't surprise me if one of the surprises is that it could definitely harbor life.
And so you think there would be breathable oxygen there, something like that gills or some sort of breathing mechanism, lungs, whatever, could actually extract from the water?
I don't know if I would go as far as lungs or gills, because I myself am only thinking about, lost city. I'm thinking about the smoking towers at the bases of our ocean. So I'm thinking about, just simple life right now. I'm not thinking about fish or people or whales or anything like that. I'm just thinking about cells that can reproduce, cells that can harvest energy and have chemical interactions and have the possibility to become more complex.
Well, Herbert would agree with you. He said there's no whales under the ice shield of Europa. So,
yeah.
Go ahead.
Yeah, I'll add a little bit to that. So one of the big questions is about what chemical energy. It's not just oxygen, because there are other ways that life can process energy in order to survive. Though oxygen for animals is obviously the major way on Earth. But how much of that chemical energy is available inside Europa's ocean? It's not communicating with sunlight like the Earth's ocean is, and the sunlight can dump a lot of chemical energy into our oceans, and that's a lot of why fundamentally we have all the amazing life in our own oceans. It's dark down there in the oceans of Europa, and it's sealed under probably several miles of ice. And so the kind of chemical you can get going, there are lots of ideas about how that might happen, interactions with the core, as Melissa mentioned. Another way you might get energy into the interior is by cooking up chemicals on the surface and then bringing those down into the interior. And in fact, it just so happens that I'm in the middle of an observing run on a telescope in Arizona, looking at oxygen on the surface of Europa. We found that there's oxygen. There's all kinds of other rather interesting.
There's oxygen on the surface, did you say?
Yes, it's trapped inside the ice. We also see evidence for hydrogen peroxide and sulfur dioxide and quite a few other chemicals trapped in the ice on the surface, as well as a whole bunch of salt. If some of that material can get subducted or somehow otherwise brought down into the ocean, that could produce a lot of chemical energy that could be used to power life in the interior. But one of the big goals of the Europa mission is to understand that chemistry better, understand what the processes that do exchange material between the surface and the ocean, and try and get a feel for what kind of energy budget there might be for life down there below the surface.
So I was going to ask about the mineralogy on the surface. So there's observations from our vantage point looking at that. Does the Clipper have some instruments that also look at mineralogy then?
Oh, absolutely, yes.
So which okay, John, which instrument?
One is the mass spectrometer that Melissa's working on. I guess that's more about the chemical elements on the surface, because by the time they get blasted up into space, you're mostly dealing with fragments and molecules rather than complete minerals. But that gives you a pretty powerful indicator as to what the stuff is on the surface that's being broken down and knocked off for the instrument to measure. We also have a dust detector that will be looking at dust particles knocked off the surface, either in plumes or just by meteorites hitting the surface and knocking stuff off, and they can measure the composition of those dust particles. And then the big gun really for that is the near-infrared spectrometer that will be looking at the reflected light from the surface, kind of like I'm doing with the telescope at Lowell Observatory at the moment, to look at the fingerprints of minerals on the surface and see how they vary from one place to another. So that's a pretty powerful technique that we'll be using.
Okay, Venom 7111 is asking a good question. What would be the preferred power source for the rover? And I'm going to extend that to the spacecraft, since I'm guessing solar would be improbable. And Philip W. answered that and said it would have to be nuclear. There's no other option that gives good enough energy to usage ratio. And that's actually not true, because Juno is solar powered right now. So how are you going to power the Clipper spacecraft?
Well, Europa Clipper is like Juno. It's going to use solar arrays and use solar power. And I did just want to add that we don't have any plans for a rover yet on Europa.
Right, that's the lander part coming later.
We're just going to land, but I'd say undoubtedly the lander has to be nuclear. So, but the decision was made for Clipper that solar is adequate, and so that's what we're going to use for the Clipper mission.
Okay, so to sort of split it up for spacecraft in orbit, solar power is fine. But to land, you would need probably another power source. Good. Okay. And Yurik Mazino is saying, I'm confused a bit. So beneath the rocky crust, there is a rocky mantle. In that case, there can't be any subduction plate tectonics, can there?
Mm-hmm. Well, I may have said something that was misleading, but I'll just start from the top and work and try and say it right this time. So we have an ice surface.
Maybe that globe.
Yeah. Yeah, here we go. All right. Ice surface. This is what we see. And we know it's probably, tens of miles thick or a few miles thick anyway. Underneath that, there's an ocean that may be 50, 60 miles thick. And underneath it, we have rock that extends most of the way down towards the interior. I don't think we really have really good nomenclature for divisions within that rock. We know very little about it because we can't see it. It's all very indirect. And so if I talked about the rock being divided into a crust and a mantle, I probably was misspeaking there. I'm sure there's a lot of structure and a lot going on there, but we don't know enough about it yet to give names to different layers in that region. And then actually we think there's probably a metal core in the center, kind of like the Earth has a metal core, but a lot smaller in proportion to the size, because some metal would have been incorporated into Europa as well. But we don't have really good constraints on that at the moment.
Excellent, Yurik. That shows you were listening. Good. That was a great question. Thank you. Let me check in with Carl. Carl, anything I'm missing? You're muted, by the way. There
we go.
There you go.
There are a couple questions that I thought were kind of interesting. I know we touched on the future lander.
Okay, can you read who the question's from and what platform, please?
It was on... It's on the Google Hangout. Let me see if I can find it. I couldn't copy down their name.
Okay, go ahead and just ask
but they were asking about... here we go. Bjorn Larson. What's the best place to land? Oh, sorry. What's the best place to land? I know that we talked about, trying to find shallow places where the ice is thinnest, but possibly from an orbital mechanics standpoint, where would be the best place to land? The equator, the pole, does it really matter? Those kinds of things. And if it matters from a geologic standpoint, that would also be interesting, I think.
Good question.
Well, I'll just start off by saying that we actually really don't know right now because the Galileo mission only mapped a really small percentage of the surface at high resolution. So you really have to have, high resolution imaging to tell where you should land. And we really don't have that for most of Europa. And so, I think though that just generally speaking, it's going to be someplace where we think there's current activity. Either there's been the ice crust has collapsed and we can tell that from images, or there are ongoing plumes and we know for certain, that's a good location. But part of the goal of the Europa Clipper mission will be to get good imaging of the whole surface and to help scout out where would be good places to land.
Okay, good.
There was another one from Andrew Planet.
Andrew, welcome. It's good to have you back.
This is a life question about abiogenesis. And he says, we are still not sure if life originated on Earth or arrived here extraterrestrially from comets and the like. Could there be different pathways for life to start rather than any single one? So like once whatever the first self-replicating molecule is, I guess maybe are there different chemical configurations for those replicating proteins? Or could there be an abiogenesis event on Europa or a world, and also there be a panspermia event simultaneously? those kinds of really speculative questions, but it's cool. I think it's a cool question.
Yeah, these are huge questions, of course. They're fundamental to understanding why we're here on this planet. And that's a lot of why we want to find out about if there's life elsewhere and what kind of form that life might have. Is it similar to Earth life? Is it completely different? And it's so speculative at the moment because we just don't know how life formed on the Earth. We have a lot of interesting ideas, but we really don't know. We don't know if it's something that was incredibly improbable, in which case you might have 1 billion Earth-like worlds in our galaxy, and this might be the only one with life because there's just something incredibly unlikely has to happen to make life get started. Or it could be it just is easy and happens all over the place. And so looking elsewhere is going to, and looking for signs of life is going to help answer those questions. And the Europa Clipper isn't going to find life on Europa unless, we do find whales poking up their heads through the ice or something. So it's only the first step in that process. It's going to be learning about whether there is an environment that life could exist, and then there'll be follow-up missions if it continues to look promising. But yeah, these are the big questions we really want to know the answers to.
I guess a quick...
Go ahead, Carl.
A quick follow-up to that would be, I think, would there be a way to tell chemically that this life formed fundamentally differently than, say, life on Earth, or if there was a abiogenesis event and a span-perm event on the same world? Are there ways chemically of telling the difference?
Oh, certainly if we can lower a DNA sequencing machine into the ocean. And, once you've got this stuff in your lab, you can answer all these questions. But with the instrumentation on this mission, or even on the lander mission, I think it will be hard to answer those questions. But they will point us in the right direction. Or we might just be completely surprised by something out of left field that gives us answers where we weren't expecting to find them.
The whales.
I gotta tell you, listening to this hangout and some of the recent hangouts I've done. The what?
Minnows.
There you go.
Hey, why not go big?
Yeah, but these are amazing times. We've just discovered that there are planets out there around other stars in our own galaxy, and now here we are talking about whether we're going to find life within our own solar system, whether it's easy or hard, whether life is common in the universe, and we're really on the threshold of finding this stuff out. Now, you said the Europa Clipper is not going to, land. We are going to get an idea of the environment for Europa and whether life is possible or not. So when we go to build this thing, I guess we want to go back to the mission itself. You said the mid-2020s. We're going out there.
Hopefully early.
Hopefully earlier. Take a few years to get out there. Are we building it now, Melissa? Or is it being built, constructed right now? The only thing left to decide would be the rocket and things like that?
Yes, absolutely. It's, it's got funding. It's passed... the major milestones for NASA mission development, and the instruments are being built. I don't know that the spacecraft is actually being built right this second, but but it's.
I think there are some things that take a long time to procure and get started with, and I think they're starting to work now on some of those long lead time items that. Some of the hardware that will eventually go into the spacecraft. But the final design of every nut and bolt isn't complete yet, and that will be completed in the next year or so. And at that point, then the construction will begin in earnest. So now there's the beginnings of that is happening, but there's no spacecraft sitting in the high bay at JPL yet that we can.
Is JPL building it?
Yes.
Okay. All right. So Attack is commenting, we just found out there's other planets. It's obvious? Actually, no. I meant planets around other stars. And it wasn't obvious just 25 years ago that there were other planets around other stars. So it wasn't obvious at all. But now we know it's a very common thing. I'm starting to wonder. I used to be of the opinion that life was a very difficult thing, that to go from no life to life was a very hard thing to do.
That,
and that we wouldn't
might
find
be
it.
true for you personally, Tony, but
No. Well, you know what I mean, right? I mean, it's
yes, I'm just.
but now I'm not so sure. Now I'm starting to wonder
No, it's everywhere.
I know you're coming around to my way of thinking.
So you think it's everywhere? You think we're going to find it in several places in our own solar system? And
I don't know if it's everywhere, but I would be very surprised if it's in only one place, and that's the Earth.
well, okay, but if it
I
is,
would be shocked.
but my argument is,
we were the only example.
well, okay, but I'm just going to say that if we do find another independent example here in our own solar system, then I would argue it's everywhere because there's nothing special about us, and if we got two examples of it, we're probably going to find it all over the place.
Right, which is why it's such an important question to answer. But yeah, I mean, I think I'm more the other way that because we don't know how life forms, and it could require some incredibly unlikely step. The right 32 amino acids all have to come into the same confluence at just the right time in order for the thing to get started. It could be that it's very rare. I mean, I don't like that idea. I'd much rather think that we're not alone in the galaxy, but we won't know until we find examples elsewhere.
Well, with billions. I'm sorry. Go ahead,
But
Melissa.
it's also true that.
I was going to say we can have all the opinions we want, but in the end, we have to have evidence.
Yep.
So we can all have fun sharing our ideas and our opinions and trying to, base our guesses on what we know. But until we find evidence, we really don't know. So.
Tom Cruise said, "Show me the money."
Did you want to add something, Carol?
I was just going to say I appreciate your point, John, that it could be difficult. It does seem that once it gets going, though, man, it shows up everywhere. I mean, there's been a lot of work trying to find places where there isn't something on the planet Earth. So once it gets going, it looks like it goes everywhere.
All right, well, we're out of time, and I'm going to let Ryan Korniloff sign us off with his comment. He clarifies, intelligent life is difficult. Look how difficult it is to find on this planet. So with that having been said, I'm going to stop us there. I want to thank everybody. I want to thank our guest, Dr. Melissa McGrath. She's a senior scientist at SETI. She's a co-investigator also on two of the instruments on the Europa Clipper mission. Also, Dr. John Spencer from the Southwest Research Institute. He is working on the Clipper mission, as well as he is very active in New Horizons. So thank you guys so much for taking time out.
Great. Thank you for your time. I know
great
you're
questions.
It was a lot of fun.
Yeah.
Thank you so much.
Okay.
I appreciate we finally got you here.
Yeah. Okay. So we will be back next week, next Thursday, with the Future in Space Hangout. I'm sorry, but I don't have the topic, but we are going to be back next week for that. Carol, thank you for setting this up. This was an amazing hangout. This was a lot of fun. Thank you so much.
Sure. And we'll be doing something on exoplanets. 2 exoplanets, very similar in size and near their parent star, but very different in atmosphere. Why is that?
On the next Astro Coffee? Awesome.
Yeah.
Okay, great. All right. Well, thank you guys very much. On behalf of my guests, I want to thank you all for watching, and we'll see you guys next week. As always, keep looking
up. Thank you.
Bye-bye.